All right, let's get started. Hello again, everyone. So let's actually jump to the document of what we're going to be doing today. So we're going to be looking at conic sections today, and maybe even another section as well. But just before that, I just want you guys to know that the mock test for test 2 is up. And so you guys would actually know everything. Now, your last few quizzes were actually pretty good practice for the test. So you do know enough right now to take that test and hopefully do well in it. So I would suggest that by tomorrow to go through that test. So you might spend the rest of today, maybe the early parts of tomorrow, just brushing up a little bit, making sure that you have everything under control and all that good stuff, and actually attempt the test between tonight and early tomorrow, or even late tomorrow, so that by Friday, if you have any questions that you want to ask me or any issues with the test, we will devote a small section of Friday to those questions potentially. So I think that is a good game plan. So the test is up. I do think you should take it as a test. So meaning study, and then when you're ready, put all your notes and books away and time yourself and actually take it, see what you actually know. I did not post the solutions, and I don't think they will be up in time for the test, because right now I'm more focused on getting everything online, getting all these tests that I have in the online platform that I'm doing. So I don't think I'll have time to actually write up solutions to all the finals and mock tests for all my classes and post them in time. So for the most part, just go through it. And if you have questions, we'll devote a little bit of time to that in class on Friday. And of course, you can see me in office hours on Friday as well, or send me emails. And yeah, hopefully then by Tuesday, you'll be in tip-top shape to do well in that. I don't anticipate it's going to be an issue, provided that you've actually been doing the mock quizzes I've sent and you showed up to recitation and actually get your questions answered there. So as I mentioned, it covers series, everything from series. So checking whether a series converges absolutely, conditionally, or it diverges, finding radius and interval of convergence of power series, finding a power series of a function using a known power series. And remember, there are 4 of them that you should know. The ones for e to the x, cosine of x, sine of x, and 1/1 minus x. Using those, you should be able to develop power series for other things. Finding a power series from scratch using the formula from the Taylor series is something you should know. Also knowing how to use series to evaluate integrals. And then there'll be a couple questions on parametric equations and polar coordinates, the easy stuff, like converting coordinates from rectangular to polar and vice versa, and describing regions in polar inequalities. So I think that's pretty much it. That's what you'll need to know for the test, which.
Sorry, I had a question.
Yes.
How long is that? So I wanted like practice the test at home, but how long would the actual test be?
Yeah, so it'll be during your recitation. So you should budget 50 minutes for it. Now, I think the practice test I wrote to be a little bit longer. So I'll say for the practice test, take 60 minutes, take an hour. But you definitely want to be in that 50 minutes / an hour range. It's going to be around there. It's going to be like a regular test. I'm not making it any harder or
All right, and
that.
the regular test we would take on paper, and then we just scan it or whatever.
Yep. Yeah.
All right.
So, and yeah, so I'll send you more details on that as well. But yeah, the test is up. I actually also listed the topics in the review section for the test. So make sure you read all the topics that I mentioned are on the test, and make sure you actually feel like you know how to do them, then take the test and see how you do. And then you can discuss with me afterwards. But if you've been going through the quizzes, it really shouldn't be a problem. Yeah, that being said, let's actually continue. So today we're going to talk about conic sections. And it turns out conic sections are really cool, and they're actually very applicable. However, it turns out in the academic setting, you never really use them for anything useful. So that's just one of the blind spots in academia. But strictly speaking, it's not a big blind spot because it's not like they're terribly complicated to work with. But if you're interested in some applications about conic sections, I put a nice little YouTube video right here that will show you some cool things about conic sections, and it will mention some other ways in which it's used. For us, though, we're going to do a very brief treatment. We're just going to run through it, and it's not going to be comprehensive, and it's not going to be a good thing at all. In fact, there are quite a few things in this section which I'm just going to assume you guys know and move forward. What I really want to focus on in this section is sketching certain conic sections. And even when it comes to that, I'm going to expect you to know how to sketch a few of them. For example, a circle is a type of conic section. I'm not going to teach you guys to sketch a circle again. I would assume everyone in this class knows how to sketch a circle, especially if I give you the center and radius. A parabola is a kind of conic section. I assume everyone knows how to sketch a parabola. But the other ones, I mean, it's probably not a big chance, but there's a fairly decent chance that the average Calc 2 student will either not know or not remember how to sketch an ellipse or a hyperbola. And so those are going to be the two main focuses of today. So I'll talk very generally about conic sections, what they are, all the information that you would need to know about them. The more technical details is in the notes in here, but our focus is just going to be learning how to sketch a couple of the ones that I think there's a good chance that you might have forgotten or never learned how to sketch in the first place. And this is really, so I'm going to touch on sketching these in this class, but it's really to help you guys with the next class, because when you go on to Multi-1, Calculus 3, you're going to be working in 3 dimensions. And a lot of times, just to get your bearings, you're going to need to learn how to sketch things in 3 dimensions. And it turns out the secret to sketching things in 3 dimensions is to be really good at sketching things in 2 dimensions. And at that point, it's going to be important for you to know how to sketch various objects, how to sketch a line, how to sketch a circle, how to sketch an ellipse, how to sketch a hyperbola, because you're going to take all these 2D sketches and combine them to create a big 3D sketch in order to figure out some problem. So there are some very common types of surfaces that you'll encounter in the next class in Calc 3, where in order to draw them and kind of know how they're going to behave, you will need to kind of know about conic sections, and that's going to help you. So just for visualization purposes is really what I want to talk about. I'm really only going to cover enough here that's going to help you set up problems in the next section, but it's not meant to be comprehensive. So that being said, let's actually move on. And as always, to minimize the risk of glitchiness, I'm going to turn off my video. And so you guys can just listen to the soothing sounds of Jhevon's voice teaching you mathematics. Okay, so why are they called conic sections? It turns out that these are shapes that you can get by slicing up a cone. Now, a cone is a mathematical object. You can imagine it lives in 3 dimensions, and we'll probably talk a little bit about that, but not much. So imagine that this is the X, Y, Z axis. A cone is just an object that goes like that, but it goes on forever. And it also goes on forever in the other direction, right? Now, it turns out you can take a plane and you can actually slice through this thing and achieve certain kind of curves in the cross section. So as you can see over here, there are examples of us slicing through the cone with a plane, which is a flat 2-dimensional sheet, which has, well, it's not exactly correct to use the word slope here, but it has the same slope over every point. You'll know how to determine the direction of a plane in Multi-1 as well. So it turns out if you slice across the axes in a certain way, you can actually create certain curves that will be along the outline of the cone and the plane. So for example, if you slice perpendicular to the axes on 1/2 of the cone, you will achieve a circle. If you slice at an angle, going through the dot here is sometimes called the apex of the cone. If you slice a plane and you don't go through the apex, but you slice it at an angle to the axis, which is this vertical line here, you will achieve what's called an ellipse. If you slice it in such a way that there is no actual end point on the other end. So here, all the way around, it's bounded, but notice it's possible to slice a cone so that this curve will actually continue forever. That is what causes a parabola. So that shape is going to give you a parabola. If you slice it parallel to the axes, but not through the apex, you get kind of almost two parabolas. They're not going to be quite two parabolas, but you get one going down and one going up. That shape is called a hyperbola. Now, there are such things called degenerative conics. This is when you slice it such that the slice goes through the apex itself. This can either result in a point, or just one straight line, or two straight lines crossing each other in an X. These guys are called degenerate conics. And for us, we're not going to care about these. Now, they do show up in multi-1, but whenever they show up, it's kind of the situation where you can ignore them anyway, because when you try to sketch them, when one of these guys show up, they're kind of going to be covered up by the other things that you're sketching, and you can essentially ignore them actually. It's not going to actually, they're not going to matter that much. Knowing how to sketch a circle, an ellipse, a parabola, and a hyperbola is going to be very important, however. So I want to make sure that you guys actually know how to do that. Now, circles, which is this situation over here, and parabolas, I'm going to assume that you know how to actually deal with those guys. Now, I do go down, and here's where I give a different angle of you seeing how parabolas and circles and ellipses and hyperbolas would come up. Now, I do go down and I give you some details about parabolas and how it opens up and down, and we know that. I even give you more information that you will tend to need, like what the focus and the directrix is and all that good stuff. Let's not talk about those right now, even though. So a parabola, another way to think of it is not as a conic section, but it's like a curve that is equidistant from some point, which we call a focus, and a straight line, which we call the directrix. And if you try to map out all the points that are, if you have a point and this line, which we call the directrix, try to map out all the points that are the same distance. So if I measure the distance from the point to the line, it's actually the same as the distance from that point to the, from this point to the curve is the same distance as the curve to the line. And this will be maintained no matter which point along the curve I sketch to, right? A parabola is a graph that does that. So that's what these guys are. Don't have to worry about that. Basically, if you have this equation, you should know how to figure out how to sketch the parabola based on that equation. You should also know about ones that open left and right. Not going to go over that. So the first guy that we want to focus on is the ellipse. And like I said, all the details of what you would ever need to know about an ellipse are here, but we're going to ignore them for the most part. I really want to actually focus on how you would go about sketching one of these guys. That is potentially something that a lot of you won't remember. The next section, I talk about hyperbola. And of course, circle is the last section. I'm going to essentially skip over that. But let's focus on ellipses and hyperbolas. I want you to know how to come up with a picture for one of these equations that you might have. So here's how these guys will actually work. I'm moving the chat box out the way here. Okay, here's how one of these guys will actually work. So this is the equation of an ellipse, right? In this case, the denominator, the thing that's under the x, the b, right? So it's a b squared in the denominator. The b is assumed to be smaller than the a. Whenever the larger number is under the y, it means that it's like a circle, but it's stretched along the y, right? Whenever the larger number is under the x, it's like a circle, but it's stretched along the x, right? So let's look at either one of these situations. They're pretty similar to each other. So you would have x minus h squared over b squared, y minus k squared over a squared, assuming that the a is the bigger number. How would you go about sketching that? X and Y are your variables, your typical X and Y. Your H, your K, your A, and your B will be constants, okay? Now the center, as you can see here, is H comma K, okay? And normally when you want to sketch an ellipse, that's where it all starts. So essentially, let's say we're on the axes here. So say this is the y-axis, this is the x-axis. Let's say you identified the center. Okay, so here, boom, smack dab is your H comma K. Right, so that's the center. Now, how do you actually deal with these numbers to actually get a picture? So the X, what you will do is you would look under the X and notice that you would have a B squared. The base is what's important to you, the B. So the B tells you how far you move left and right from the X coordinate of the center. So the B is going to tell you, okay, we're going to move B units left, so that's B, and B units right from the center, right? So this is how we're moving in the X direction. We move units of B. Let's actually, oh, what did I just do? Let's actually, we don't care about drawing to scale. Let's make it look a little bit more to scale. Okay, so that's how you move in the X direction. Now, you kind of do the same thing, and you're going to focus on the Y direction. So for the Y, you're going to look in the denominator. There's going to be an A squared. You are focused on the A. The A tells you how far you go up and down, right? And don't get attached to whether I call it A or B. What you want to look for is the number underneath the X and Y respectively. So you move A units up and A units down. Now, what you will actually create by doing this is you will actually create a box, right? You can now sort of imagine that these guys create a box. And what I'm drawing now, none of this is actually on the graph. It's just kind of a skeleton to help you know what the graph would look like, right? So you start with the center, you move left and right by B, namely the base number that's underneath the X. You move up and down by the A, namely the base number that's underneath the Y. This will project onto the sides of a rectangle. And now all you do is you actually draw a curve that passes through all these points. Where these lines intersect that rectangle, these will be points on your ellipse. So you're really gonna go poof. If you make the sound effects, it increases your power level. So that's how such a shape would come about. Okay. Now, hopefully that's clear. We'll probably do some more examples later, but that's how you would actually go about sketching an ellipse. And in principle, sketching an ellipse stretching the other way is done exactly the same way. It's just that this rectangle would look more elongated in the other direction. But that's essentially how this would actually come to be. And yeah. So the longer axis here is called the major axis. The shorter axis here is called the minor axis. But that's what these guys are. And I believe I put this asked you to sketch something like this as a bonus in the quiz yesterday. But yeah, that's how you'd actually go about sketching an ellipse. Both of these have the same idea. Moving down. Now let's look at the hyperbola. Now, a hyperbola starts out almost being like how you would sketch an ellipse, but it's actually also different in some significant ways. So, moving the chat box out the way again. So how do you know when you're looking at the equation of a hyperbola versus an ellipse? They actually look very similar. And again, I'll post the notes here in a PDF under the video description. But the difference is the ellipse will have a plus sign in the middle, while the hyperbola will have a minus sign in the middle. Now, a hyperbola can open either left to right or up to down. And what that determines is who is having the negative sign. Well, if your x has the positive square and your y has the negative square, it appears after the negative sign, it opens in the x direction. It always opens towards the guy who's positive. If on the other hand, you have the y squared over here minus the x squared over there, it opens towards the y. It'll open up and down towards the positive. Now let's actually see how such a graph would actually come to be. Again, all these guys, you don't really have to worry about these numbers. I'm never going to actually ask you to calculate these numbers. I'd only ask you to sketch them and maybe identify these coordinates here, which should be easy enough by just not even remembering these formulas, just by looking at adding a and b to the h and k respectively. So here's the difference between the ellipse and the hyperbola. So here's how a hyperbola is going to look. So again, here's some axes. So again, we are going to identify the center. So let's suppose for argument's sake, it's over here, h comma k. And once again, we are going to move a units in the x. Say it's that. A units to the other side. Then for b, we're going to move b units up, b units down. Let's call that b. And again, you get a box. Right, so again, this is a little skeleton here. Okay, so now you have the box, very similar to how you would have an ellipse, but this is where the similarities actually end. To actually continue with this, you are not going to actually connect the dots. You will create asymptotes. So notice that this hyperbola will have asymptotes. How you create the asymptotes is that they go along the diagonal of this box. So through the center and the top corner, there is a straight line. And it goes the other way as well. So that's also a straight line going through the corners of the box. And now is where the negative sign is actually matters. Now, let's say I'm sketching this one, right? So the x is positive. Once the x is the positive one, it means that the coordinates I move through are along the x line. So it's going to move through this and that. Otherwise, if the y was positive, it would move through the b line. But what we're going to do now is we're going to open up this curves such that it'll kind of look like a parabola, but it's not quite a parabola because it is going to be asymptotic to these asymptotes here. So the curve is going to look like you start at this point and then you extend. And it runs along that asymptote. And then for this one, it runs along that asymptote. And can I expand this a little bit? Same thing on this side. You are going to start here and it's going to run along that asymptote. And you're going to start here and run along that asymptote. So this will be symmetric, but it opens in two directions. And when it comes to sketching, that's it. That's the only difference between the ellipse and the hyperbola. So the hyperbola has these asymptotes that goes through the box, and you have parabolas. I shouldn't call them parabolas because they don't actually behave like a parabola. Parabolas don't actually behave like straight lines as they go off to infinity. But there are parabolic-esque wings to the graph, which will either open to the left and to the right if your x is positive, or you'll start here and open up and open down if the y was the positive one. So far, are there any questions about that? Anything I've said so far with ellipses and hyperbolas? I guess not. You guys can't hear me, right? I'm not talking to myself.
Sorry, no, I don't have any questions.
Okay, all right. So just say no, you don't have questions, because I do want to know. Because there's also the issue with where every now and then I've had issues with technology where the internet would just go out and I'm not even realized. So sometimes I just want someone to make a sound so I know that you guys are actually still there. So no questions, just say no, no questions. I need like an auditory or maybe even like a chat box reminder. And that's pretty much it. That's kind of all I want you to know. Now, of course, I do expect you guys to know how to sketch circles and all that good stuff. So I probably won't ask you about that. But at any given time, I could ask you to sketch an ellipse or a hyperbola. And the only other thing that you need to do on top of this is to first figure out the center and all these numbers first, because not always is the equation going to be given to you in this nice form. But just like how with circles, you can get it into this, if everything's expanded and separated, you can get it into this form by completing the square. So too, that's an additional thing that might have to happen with problems like these. You might have to complete the square to actually get it to look like one of these guys. That being said, so here I did an example. So you guys can actually try problem 4 and see if you get the same answer as this. That's what it would look like. But let's actually do another one. Let's actually go through problem 2 together so you can see. So if I'm asking a question like this on a final, it'll probably look like this. I'm not just going to give you the equation. You're going to have to do a little bit of work to get to a nice equation. So for all of these, I also gave you the answers in case you want to try some of them on your own. I'm not going to do all these examples. So let's actually look at problem 2. Let's get rid of that. Okay, so problem 2. So this is not going to be given to you, obviously. Right. I just knew I wasn't going to do all the examples, so I just put in the answers for some of them, for all of them. So whatever I decide not to do, you guys can actually try it on your own and know that you got it right. Okay, so you can have a problem like this. Identify the conic and state its center and radius. And I would say something like include a sketch. Okay, so this is how something could be given to you, right? Which doesn't look like any of the equations that you would have known from these boxes, right? So the boxed equations in here is what the formula would look like in order for you to be able to sketch this. So we are going to start by figuring out which one of the conics am I looking at. Now here the answer says it's an ellipse, but pretend we did not know that in the beginning. We are actually going to figure out that it's an ellipse. So let's actually do that. So we are given that 9x squared plus 16y squared minus 18x plus 64y equals 71. Now, of course, you know, when you want to complete the square, the first thing would be to group like terms. So I'm going to group all the x's, group all the y's. And of course, to complete the square, you are going to have to factor out the coefficient of the x squared. And the coefficient of the y squared. 16 goes into 64, I want to say 4 times. And now you want to complete the square inside the parentheses. So this is x squared minus 2x. I'm going to add, well, I'm going to add and subtract something. Y squared plus 4y. I'm going to add something squared, subtract something squared. Here I'm going to add something squared, subtract something squared. Okay, now the thing you add and subtract is going to be half the coefficient of x. So half of -2, that's -1, -1. Half of +4, that's +2, +2. And so now what happens is, the first three terms will be a complete square. It is going to be x plus the guy inside here, all squared. Then we're going to be left over with this guy, which is just a -1 hanging out. Similarly, this guy is going to be a y plus 2, all squared. Then I'm going to have this -4 hanging out. And so now what I would have is 9 times x minus 1 squared minus 9 plus 16 times y plus 2 squared minus, that's a 64, equals 71. Now, of course, I'm going to move the 9 and the 64 to the other side. Plus 9. And what's that going to be? 9 and 71, that's 80. 80 plus 64, that's 144. Okay, so now this is starting to look nice. Now, this would almost be a circle, except the fact that the 16 and the 9 are not the same numbers, so the radius isn't going to be the same. There's a stretch that's more bent towards one variable than the other. To do this, what you would do is, so once you realize it's not a circle, you want to make sure it looks like one of these equations that you'd have memorized. So you know, for the hyperbola and the ellipse, there's a 1 on the right side. So the next thing would be to divide the entire equation by 144. So I'm going to divide by 144, divide by 144. So ultimately here, I would have x minus 1 squared over, well, this will be 144 over 9, plus y plus 2 squared over, let's be 144 over 16, equals 1. So now we start to see that it's looking like an ellipse. Let's just actually make this look a little nicer. So this is x minus 1 squared. The 144 is 12 squared, 9 is 3 squared, so it's that. 144 is 12 squared, 16 is 4 squared, so it's that. And these guys can actually simplify. So we end up with x minus 1 squared over 4 squared plus y plus 2 squared over 3 squared. Now that you can identify as an ellipse, and the center is 1 comma minus 2, and you know that the major axis is horizontal because the bigger number is under the x. Now, of course, once you do that, you can actually work on sketching this. So the center is 1 comma minus 2. So maybe I should have drawn that a different way. It's going to be underneath a little bit. So let's call that 1, call this minus 2. So that's the center. Now I know I want to move 4 units in the x direction. So I'm going to do 4 units over here. So, you know, at this point, you're going to be 5, comma, minus 2. You can figure that out just by taking 1 and adding 4. Then I'm going to move 4 units moving that way. So this is going to be subtract 4 minus 3, comma, minus 2 is going to be that other point down there. Also, I'm going to move up and down by 3. So the y value, there's a 3 here. I'm going to move up by 3 units. That's going to bring me over here to a 1, comma, 1. And if I move down by 3, that's going to bring me down to a 1, comma, minus 5. So those are my points. I can therefore get this little box going. Make the sound effects, as long as you're not disturbing anybody and obeying proper social distancing protocols. And then now you just actually connect all these dots here. And so that is going to be your ellipse. Okay, and that's it. So for this section, that's pretty much all I'd expect you to actually know how to do. So if I give you one of these equations, you should be able to, using complete the square, put it into one of these forms that are in one of these boxed equations over here, which again is a lot of just algebra. Once you actually get it to one of these nice forms, I expect you to know how to actually draw it after that. And at this point, that's all I would want you to know. However, being able to do that is going to be very important in the next section and the following section of the course, like multi-1 and multi-2. So hopefully that is clear. Technically, we haven't done any calculus here at all. It's not a calculus topic, in fact, but it is. This is a topic that I think a lot of people tend to just not remember how to do. And so because it's actually important to know how to sketch things in 2D very well for sketching things in 3D, I want to remind you guys about some commonly forgotten things, commonly forgotten sketches in 2D. Now, I am hoping no one has forgotten how to sketch a circle or a parabola or a straight line or a log or an exponential or all of these guys, because you've been sketching those a lot in Calc 1 and the classes before. You get a lot of practice on those. Hyperbolas and ellipses, not so much, at least not typically. So that's what I wanted to go over here. So hopefully that much is clear. Okay, are we good? Any questions on anything I did here?
No, no questions.
No questions.
Okay, all right, cool. So that's it. That's all you need to know for this section. Know how to sketch them. Now, the next thing that we want to talk about, which I'm just going to introduce and get you kind of thinking about it for the future, is I actually did want to start looking at 3-dimensional coordinate systems. Okay, so this is kind of almost a primer to Calculus 3. And so we want to move from a 2D space to a 3D space. That's going to be important for all sorts of reasons. Of course, we live in 3 dimensions, at least as far as we can perceive. We can perceive 3 dimensions. And so being able to do math in 2 dimensions is fun and all, but ultimately we're going to want to move to something that can model the real world a little bit better. And 3 dimensions, it's where it's going to be at. Now, when it comes to 3 dimensions, there are going to be a few things that are similar to working in 2 dimensions, but actually most things are going to be very different working in 3 dimensions versus 2 dimensions. However, understanding the 2-dimensional world is going to be important but you should just be aware that things are going to be drastically different. So there are going to be certain things that are obvious in 2 dimensions that are not obvious in 3 dimensions. So I was talking the other day to some students, and one of these things was, so you think of the equation y equals mx plus b, and you would ask someone, well, what is y equals mx plus b? What is that? What kind of object is that? And pretty much any school child old enough to find their own way home would know, oh, that's the equation of a line, right? With slope m and y-intercept b. It turns out, once you go into 3D or higher, that is no longer true. Y equals mx plus b is not the equation of a line. It is actually the equation of a plane. And so there are a lot of things that your intuition would tell you that are just plain old wrong in 3 dimensions. And so being able to learn how to navigate 3 dimensions is going to be an important thing. And you have to realize that there are a lot of things that you know for a fact in 2 dimensions that they just aren't true, or they don't generalize very well to 3 dimensions. You have to kind of make some tweaks and changes here and there. So I wanted to start priming you for what some of these tweaks and changes would actually be. And that, of course, starts with just me introducing the 3D world, what it would look like, how it would behave like, how would you represent it on a piece of paper, how would you actually sketch things or locate positions in this system. And so we're going to do that. Now, in your book, it's entitled 3D coordinate systems, plural, but they only actually cover 1 coordinate system, namely the rectangular coordinate system. But by the end of multi-1, you will be able to learn, you will have learned and will be able to think in at least 3 coordinate systems, different coordinate systems. One that's kind of like a polar coordinates version that works in 3D, that's called cylindrical coordinates. And you're going to have another coordinate system called the spherical coordinate system, which any of you who are in physics would probably have seen that already. But you really start talking about that in multi-1. That being said, let's actually just talk about a few details here, just to kick this off. Just to remind you about the rectangular coordinate system. We saw this, rectangular coordinate system in 2D. We know how to do that. So if I wanted to, for example, locate the point 1, 2, so if I wanted to locate 1, 2, sure, you find 1 on the x, you find 2 on the y, boom, that's the point 1, 2. This is a rectangular coordinate system because you can see that there's a rectangular shape that results from you tracking these lines to find that coordinate. Of course, a rectangle in 2D, this one is pretty intuitive to most people, but a rectangle in 2D would actually translate to a box in 3D, right? So you might look at the same idea. Let's say we're in 3 dimensions. How do you start to talk about locating a coordinate like a 3 coordinates? So first of all, customarily, we throw in a 3rd axis, and we normally draw it like this. We call it the z-axis, so we use the letter z. And then our x drawn that way and our y drawn this way. So pretty much in your lives up to this point, you have been looking at a bird's eye view of the universe. You have been looking down on this plane. And the z-axis was actually an axis pointing out the paper into your forehead, right? So once you draw the xy plane, you can just imagine that there's actually something here that's poking out of the paper going straight up in the 3-dimensional world. So we now want to actually represent that thing, and you can do it by so. And the negative x-axis would continue to go that way. The negative y-axis would continue to go that way. Negative z-axis will go down. So here where you have the negative x's, here is where you'd have the negative y's, and here you'll have the negative z's. So this is the red line, one of the red lines that I mentioned down here, and this is one of the red lines that I mentioned down here. Now, if someone were to ask you to locate the point 2, 1, 2, 3, in the rectangular coordinate system, you would actually do it very similar to what we were doing here. So you can draw that. You start by locating the 1 on the x and the 2 on the y, And you kind of do the same thing, but now you imagine that these lines are being drawn on the floor. And then this will be the point that is 1, 2, and there's a no rise in the Z coordinate, there's a 0. And then what you want to do is you want to lift this point directly straight up as a height of 3, which means you find 3 on the Z coordinate, and there's a straight line moving in a perpendicular fashion to hit that point. This is the location 1, 2, 3. Now what you'll notice here is that there's actually a box that's formed here. Where the line that goes from the Z is running along the diagonal of that box to hit that point. But there's actually a box, right? So that's this rectangular coordinate system. So we have this thing floating in space, and that's where it's located, right? So that's one way. Now, to help visualize this, we have some visualizations, and we're going to start naming some of these things, and then we'll wrap up. We'll talk about this more on Friday. So let's pretend you're a person, you're standing in a room, and let's say you're facing the corner. Okay. So what you can imagine is the corner on the floor is the origin. Your y-axis will be running, the positive y-axis will be running along the corner of the floor to your right. The x-axis, positive x-axis, will be running along the bottom corner of the floor to your left. The z-axis is the crease in the walls where the walls meet, running straight up. So your left wall is what we call the xz plane. And it actually extends forever in all directions, but that is the part of it that you would be able to see. We call it the xz plane, of course, because it's bounded by the x-axis and the z-axis. To the right, you have the yz plane. It's bounded by the y-axis and the z-axis. And on the floor is the xy plane. So you've been living your whole life on the floor up until this point, mathematically speaking. You're always looking down at the floor. So before, in Calc 2 and below, we had the bird's eye view. And so this is how we'll situate things. Now, there are rooms. You can imagine that instead, to zoom out a little bit more, that you're in some sort of a 2-story building where you're on the 2nd floor and you're standing here. Now, of course, there's a room behind your wall, the wall to the right. There's a room behind the wall to the left. There's a room below you. There's a room diagonal over there. And below on the 1st floor, there are 4 other rooms. You'll notice that these planes actually split space into 8 so-called octants, okay? Now, the you standing in the room on the 2nd floor over here, we call that the 1st octant. This is the region in which all x, y, and z coordinates are positive. If you go behind the wall to your right, your x coordinate is now negative. We call that the 2nd octant. Move over here, that's the 3rd. Move over here, that's the 4th. The room directly below you is the 5th octant. Go over there, that's the 6th octant. Go over the corner below the room 3 is the 7th octant, and then there's the 8th octant over here. And these signs here represent the signs of the coordinates in these octants, right? So these planes actually split 3D, well, I shouldn't say 3D space. They split space into 8 octants, okay? Now the space, how it's determined is going to look like, depending on how many axes we have, but that's essentially the world that we're now living in. So no longer are there 4 quadrants, there are 8 octants. And the room that you're currently sitting in is called the 1st octant. Facing a corner is how the axes will line up this way, right? If you want to move a point in space, what you do is you find the x coordinate, the y coordinate, and the z coordinate. It is also useful to know that the yz plane is it has an equation x equals 0. because your x coordinate everywhere along this wall is going to be 0. This will have the equation y equals 0. And the floor, xy plane, has the equation z equals 0. Now, that immediately will show you a difference. Before x equals 0 and y equals 0, in your view, was a line. X equals 0 was this line. Y equals 0 was this line. But it turns out if we imagine these lines being projected out of the page, they're actually planes. So these are all the equations of planes here. And these guys, x equals 0, y equals 0, z equals 0, these guys are called the coordinate planes. So we'll talk a little bit more about this, but this, ladies and gentlemen, is the three-dimensional space. And this is what we call things in the space. And you can kind of imagine 3D space as a 2-story building where you're in one of these rooms on the second floor. And we will learn a little bit more about navigating the 3D coordinate system later on, and just learn about the differences that will ensue in terms of equations and what intuitions might stay, what intuitions might stay the same, might change. And of course, you pick up with this more in multi-1, and you pick up with it even more in multi-2, because you have a lot to learn in 3 dimensions. You've already learned a lot in 2 dimensions. But right now, we need to learn a kind of mathematics and a kind of calculus that can work in a larger space, let's say, even though technically speaking, it's not a larger space. The number of points in the XY plane is the same as in the 3D space, but whatever, we digress. We'll kind of wrap up there, and I will, see you guys in the next one on Friday. So I would say for now, the focus should be on test 2. Go check out the mock test on the class webpage. Pretend it's an actual test. Take some time, not a lot of time, because you've been actually practicing by doing the quizzes. Take some time, actually study for it. When you feel like you're ready for it, like you can ace the test, which hopefully by tonight or early tomorrow you feel that way, take the test under time conditions, give yourself an hour, and see how you do. I'll devote a little bit of time at the beginning of next class to talk about any issues that you guys have or any questions. And if you have more than that, you should probably just check me out or Rolf in recitation or office hours. And I would say that. So that's it for today. We're going to stop there. And I will see you guys on Friday. So.
Thank you.
Okay. All right. So hopefully you're all good. And I guess I'll see you around.
I'm sorry. Did you post the mock quiz answers?
I did not post the mock quiz answers, but I assumed that in recitation you guys would have gone over it anyway. So anyway, but yeah, if you have any questions about anything like a quiz or a test or solutions or whatever, you can just see me in office hours.
Oh, it was because the recitation yesterday, it conflicted with this class.
Yeah. Okay. So I think you could reach out to Rolf and ask him if he has something like what I did, like OneNote, like he saved the work, and you can actually do that. Or actually try the quiz on your own. Tell me what answers you came up with, and we can talk about it at some other point.
Okay.
But that being said, I'll see you around. See you virtually around. All right. See you Friday. Go practice for test 2. I would focus on that right now.
Thank you very much, Professor.
All right. Take care.